Thank you. Thanks, Irina, for setting up the wonderful stage. And my name is Yuanyuan Su. I'm assistant professor from University of Kentucky. And today I'm going to talk about some of the very fascinating observations we obtained with multi-wavelength observations that are in galaxy clusters in a very turbulent environment. And we want to understand what is the role of turbulence. Okay, so since we're in California, today I want to start my talk with this California nebula. I think it's obvious where the name is from, but I can see this is it's a nebula very close to our Earth, and it's shining H alpha and also shining H beta. And we believe that the reason it glows is because of this very bright star, okay, to the right, and it's 07 star, it's photoanalyzing it. And in a cluster environment, we also see many cases with H alpha emission, but in those cases, as I'm going to show later, as you can see that what is responsible for it is not so clear. So for galaxies in clusters, and the clusters obviously provide a very important environment in modifying the life path of galaxies. And the most outstanding examples are jellyfish galaxies, and actually that one looks like California too. And so you can see that in jellyfish galaxies, it has a very spectacular stripped tail. And this one is showing, the top one is showing H alpha, and the bottom ones you can show that we found this tail can be observed in every wavelength. And it's a little bit counterintuitive. It's where the tail gas is from. You may think, okay, that's from the stripped gas. It's actually not that simple. You can see that this plot is they showed that which phase of gas dominates which part of the galaxy. And I want to draw your attention to the red part. Okay. The red part is shining, is dominated by CO, so it's tracing the molecular code gas. That's the coldest density phase of the ISM. And you can see that it appears at the bottom of the tail, very distant from the disk. So we think that this gas here is unlikely to be stripped from the disk. It's likely to form in situ in the tail. And I found out this very insightful simulation, and they simulated a jellyfish galaxy. And then this is a molecular gas, and they found two very obvious gas clumps, A and B. And it's really interesting that in this simulation, they found that those two clumps only showed up towards the very end of their simulation run. Okay. They are formed in the tail, not stripped from the disk. So beautiful jellyfish galaxies shining multi-wavelengths, and a recent group led by Professor Sun's group, and they found out there is a very beautiful correlation between H alpha surface brightness and X-ray surface brightness. They studied 18 jellyfish galaxies, and they show a very tight correlation between those two surface brightness. And they found out that this slope, okay, is different from the slope when they study the disk. They found out the slope for the same H alpha, the tails, has more X-ray emission. Okay? And what is happening here? And again, I want to refer to this very insightful simulation paper. They simulated a jellyfish galaxy. And they found out that they think that the mixing between the interstellar medium and the surrounding intra-cluster medium could be responsible for this correlation between H alpha and X-ray, and responsible for a different slope that is from that of the disk. And what is powering H alpha? So because it's a simulation, they know everything, right? And so they found out that, so if you simply take the estimated star formation rate from the H alpha luminosity, and you get the star formation rate as shown in the dashed line for the tail, the blue one, the blue dashed line, and the solid blue line is the intrinsic star formation rate, actually the actual star formation rate. You can see there is a huge discrepancy. Okay. So H-alpha emission in this case is not powered by photonization from the young stars. It is something else is responsible for it. And the author thinks that it's likely to be a combination of collisional radiation, and also there is a heating due to this mixing from the intra-cluster medium. It's very hot, and that could sort of mimic the process of like photonizing the cold gas. And that's very beautiful work. And so we sort of have some understanding in both in observation and simulation. And I would say that the stripped galaxies is not the only environment in galaxy cluster that we see multiphase gas. Another very well-studied environment is the cool core clusters, and you can also see this is, I took this picture from Yuanyuan's paper, and the gray one is the X-ray emitting hot gas, and the colorful ones are H-alpha filaments, and sort of similar to the tail in some sense. And so we ask ourselves, what is the response? Can we recover similar correlation in cool core clusters as the jellyfish galaxies? So this work is led by my former in the audience today. And so Valeria, before she joined my group, she's already a world-class expert on optical and CO observation cool core clusters. And since she joined my group, she has expanded to X-ray observations. And now she is really a leader of multi-wavelength observations of galaxy clusters. And so, and you can see those are some of her papers published in recent years. And so in galaxy clusters, we see a very wide range of gas and traced by different methods, and can be, in addition to X-ray, and there is also 10 to the 5, 10 to the 4, and also down to the 100 Kelvin gas. And so we try to do the same thing as this study. Okay, we try to follow this method. At first, didn't work. Okay, it didn't work. We don't see any correlation. We just find where the filaments are, then we measure their X-ray luminosity and H-alpha luminosity, and you can see that there's a large scatter. And I think that's not surprising. It didn't work at first. This is a typical image of cool core clusters. You can see how busy it is. It has a very bright X-ray halo. On the top of that, there's cavities, and there's maybe jets, and there's sloshing cold fronts, and just so much going on there. And so we have to try something clever. So we borrowed this method from the Planck community that to decompose the events into different components. And for this purpose, we didn't just use the imaging for Chandra. We used a combination of imaging and also spectrum and information. So together we form a 3D cube. And actually before this work, we never thought about looking at Chandra data in a sense of like a cube. And and you can see that this very clever method allow us to isolate out what is associated with X-ray filaments, and from the rest of the cluster, like X-ray cavities and sloshing spirals. And with that, it actually make a huge difference. And so those are some examples. And the left column is original cluster emission with everything in it. And the middle one is what we isolated out that corresponding to the X-ray filament. And we find out the right one is the H-alpha filament. We find out the middle panel and the right panel, we find out they are strikingly like similar in both morphology and also spatially correspondence. And now we can refine this plot, X-ray luminosity versus X-ray surface brightness with F surface brightness, and this is what we got. This is what we got. Okay, and just I plotted together with the observation people obtained from the jellyfish tails, and those two plots, and it's so beautiful. Not only that both of them are correlated, it's also because they follow almost exactly the same slope. Okay, and actually it's very hard for us to visualize it because the solid line is our best fit. And this dashed line, gray dashed line, is the best fit from this jellyfish galaxy result. And they just almost overlap. It's just so hard to see the difference. And there is something really, some very intrinsic connection between phases of different phases in different environments. And so we found out this very sort of also very insightful simulation, and you can see that the top one is the top one is HR5 emission, and the bottom is X-ray, and for cool clusters at different stages. Okay, and they do not always correlate, but definitely at some epochs. At some epochs, they at some time they show some very strong correlation. So this one explanation is that this code filaments is condensed out of the intra-cluster medium, and the AGN feedback may provide the initial perturbation needed to seed the local thermal instability, and also similar to the tail, it also requires a mixing of the code with the intra-cluster medium, and to this mixing could bring down the cooling time and make it help it condense. Okay, so so again, I want to so it's not I have to say it's not the first time that the people realize there's some connection between X-ray filaments and HR filaments in cool clusters. But our study is truly the first time we show a quantitative correlation between those two. And you can see that early studies, they may focus on one cluster or just one filament. You can see if you only study one cluster, the scatter is huge. You are not, even you use any clever method, you don't see any correlation. The reason we achieved this is because we managed to study a very large dynamical range. Then this relation just beautifully showed up. And also I want to emphasize, go back to our old question, what is powering this HR emission? The short answer is we don't know, but we know what is not powering it. So one argument is similar to the tail, that we know that there's not very little star formation going on in those filaments. And so we don't think it's from young stars. And another thing we think we can sort of rule out is we don't think it's related to AGN, because our filaments, it has a large span of radii. Some are really close to the cluster center, some are at larger radii. And we don't find anything like radius dependent. Okay. If it's powered by the AGN in the center, it should have a strong radius dependence. And also, this is the first time that we demonstrate there is a connection between cool clusters and jellyfish galaxies, two very different environments. And I think our work has also allowed a direct comparison with the simulation, and down to a very small spatial scale that is not achieved in previous studies. Okay. And so I think you are maybe still admiring how similar those two relations are and trying to digest it, try to understand why. But I just want to emphasize that they are not exactly the same. There are some key differences I think it's worth paying attention to. What are the differences? One difference is this, like studied by Yuanyuan and our organizer, and so she compared the velocity structure function of the quark clusters and the jellyfish galaxies, and you can see that the jellyfish galaxy is very well behaved, and it follows this Kolmogorov relation, but the quark clusters is very naughty. It is steepening. And this one explanation that, okay, there's this quark clusters, they have experienced a recent aging outburst, has disrupted the velocity structure function. And another key difference is the scatter is different. So the quark cluster is different, has larger scatter. And you may, as I have to say that some of the scatter may be artificial, maybe our method is not so ideal and like to isolate out filaments. But some of the scatter is definitely real and it's very meaningful. Like this study is by for a jellyfish galaxy. Okay, it's not plotted here, but you can see that the blue line are like the slope for regions diagnosed from BPD diagram for regions analyzed by liners. And the red one is the region that is star forming according to BPD diagram. You can see they follow different slopes. Okay. So the scatter is physical. And so our next step is trying to understand more what causes scatter. Another really key difference I found super interesting is that so for jellyfish galaxies, and the tail of the pressure of the tail is usually bigger than the surrounding intra-cluster medium. And a very extreme example is this very interesting orphan cloud. Okay, and we believe it is the end result of stripping of jellyfish galaxies. And you can see that its pressure is even 10 times the surrounding. Some non-thermal pressure needs to be in the intra-cluster medium to keep it there and to protect it. However, we find something opposite in quark clusters. In quark cluster, we found out that the filaments, the multiphase filaments, is under. It is the surrounding intra-cluster medium has higher pressure. So any non-thermal pressure support, turbulent pressure or magnetic pressure, needs to be inside the filaments. And so our group has also like moved down a little bit. In addition to jellyfish galaxy clusters, we sort of expanded to some lower mass systems, like our graduate student Ryan working with me and Valerie, and he has studied isolated, really low mass early type galaxies, and he found out yes, some of them show filaments like quark clusters, but many of them like show just a disk, okay? Also in multiphase. And very interesting that Ryan found out that those are like look like quark clusters. So for filaments, they have axis X-ray luminosity, okay? And those ways show disk structures. Their disk is kinematically and highly correlated with the stellar component. So we think it means that for early type galaxies, the multiphase gas have different origins. Some of them are from the condensation pod gas, like quark clusters, and like jellyfish galaxies, just from the stellar mass loss. Ryan is currently expanding his sample, and so stay tuned. Oh, okay, thank you. And in the end, I just want to zoom out a little bit. The reason we care about turbulence is the picture is bigger than just the tails and the quark clusters. And over the past couple of years, my group has been working on the dynamical state of the PhD student Arnab, and he has studied the baryon fraction and for ultra radius for different systems, you can see that they do not agree with the cosmic baryon fraction. And we got the baryon fraction based on hydrostatic equilibrium assumption, so maybe the assumption is wrong. And also my other PhD students have applied some machine learning technique to predict cluster mass from photometric optical data and compared to the mass obtained from X-ray and SZ. And so I know it doesn't look very beautiful, but we apply to real data, tested and trained on real data. Okay, and all those could affect the applying utilized clusters for cosmology. And another thing, we are also super interested in the chemical distribution of the intercluster medium. And in this case, we found out a cool cluster which doesn't have a BCG in it, and it is metal. If there's no underlying dark matter halo, how does it survive? And also, we studied intercluster medium, the chemical distribution out to the Vere radius, and we are interested in how well the gas is mixed in the intercluster medium. And I'm sure that the turbulent mixing could potentially provide a very important role. And we are trying to understand it more. And with that, I'm going to end my talk here. Thank you.
So first a comment. So I think this result, it shows the correlation between X-ray luminosity and H-alpha is very interesting and very important. So a question on this. One suggestion that you offered was mixing of the gas in around pressure stripping tail in the surroundings. And you quoted a paper by Lee et al. Mm-hmm. Morphology of this tail suggests that there are no magnetic fields in the simulation. So that's just a clarification question. Is that the case? These are just pure hydro simulations?
Yeah, I believe so. I believe so, yeah. And it's very interesting. They actually show some scatter, I would say, in their simulation. You can see like this ranging is definitely like no correspondence on H-alpha in it. So yeah.
All right, thank you.
So along similar lines, I guess, I would totally, I mean, this is very cool to see and very, very cool work. This correlation is, I think, kind of totally expected in the case that this is coming from mixing of these two phases, mm-hmm. and that you would, the same thing that's giving energy that is to the X-ray emitting gas is also giving energy to the H-alpha emitting gas. And sort of related to something that I mentioned yesterday is that most of the soft X-ray emission is coming from that sort of lower temperature, higher density gas at these interfaces. I wonder if you see along those lines, if you change your X-ray to only the harder energy X-rays, if you see a similar correlation.
We haven't tried that, but okay. it's worth trying. Because
my expectation it would be if it's coming from the mixing that if you move, wouldn't see it nearly as good of a correlation, and that could be
yeah okay yeah. I think also I think this paper, the relation plotted here, they use the higher energy band,
right, so that's changing, and I guess I just want to say that this is really interesting because this is actually probing, if this is due to the mixing, this is probing all of the complicated mixing physics that I was talking about yesterday, and so we should try to reproduce this.
Excellent.
Yeah, actually, I agree with everything you just said. Yeah, this is so beautiful, and I do think that even though on larger scales, the structure functions are different. When I basically treat these filaments as tracers, I think on smaller scales we're looking at the same kind of mixing layers. So I think this correlation reflects the small scale physics rather than on what these filaments are doing on larger scales. So I see more similarities between the cluster center filaments and the strip tails. Another question is, I think you mentioned H-alpha to CO ratio. I'm sure I've asked you this before, but I forgot. Do you see also a universal ratio for H alpha to CO, and if so, where is it? And if not, what do you think is the reason why?
It's ongoing work, and so Valeria is working on it. She has some very beautiful ALMA observation that reach a very small scale, and I would say that in typical our impression that H alpha filament is more extended than CO filaments.
Yeah.
And there's two reasons. One is that there were CO filaments, they just got destroyed more easily, and the other reason is they just didn't form on larger radii, and we don't know which one is real yet. But we are looking forward to the ongoing work by Valeria.
Thank you. Thank you.
So yeah, I've been obsessing about these things for 30, 40 years. And one of the, you've indicated one of the hard questions, one of the thorny questions is what powers the filaments, because that also affects the interpretation of the spectra. And bright line diagnostics that we all know and love are usually calibrated on star formation regions or AGN. And so the caution, when you go into trying to find the metallicity of the filaments and so forth, the answer to the question what powers them is really important. Also, some of the answers to the questions are also in the old literature. When we first found the 2000 Kelvin or 1000 Kelvin H2, that's vibrationally excited molecular hydrogen, it's ubiquitous. All the H alpha filaments we attempted to see, it was actually a cloudy night project. They were so bright, like 2% of the H alpha would be coming out in these H2 lines at 2 microns. This is not seen in star formation regions, right? Yeah. Another real bright signature is H2 rotational lines. Another thing, not seen in any star formation regions, but super bright in these and absolutely uncorrelated with their star formation signatures. There are some of these that do have star formation, so don't take away the message that there's no star formation going on. Some of these are forming stars at hundreds of solar masses per year, so are some of the brightest things in the local universe, in terms of their star formation rate, but they're not assembling their stars now, so their specific star formation rate is basically quiescent.
Yes. So the sequence they are low, but their star formation rate is actually very high.
So one of the biggest puzzles is the gas is dusty. The emission line gas is dusty. So I know you guys have been thinking about this too. And how you get dust to survive in the hot medium. Even a tougher puzzle, something I've been pounding my head against since I saw Spitzer spectra, there's PAHs in these systems. And the PAH lifespan in the hot medium is like 100 years, right? So the dust can be tough, okay? But in the hot gas, it's like 10 million years is the sputtering lifespan. But PAHs are really super fragile. And we see PAHs in these systems, and so will James Webb. So they're going to discover it. But Spitzer was there first. But it's going to be spectacular because these things light up like a Christmas tree in the infrared, and so I'm really excited. There's some observations with a big group of people. I'm way down on the COI list, but Abell 2597 is one of those with James Webb observations that are coming, and there'll be more in the pipe because James Webb has a long way to go. Wait a minute.
Yes.
Okay. But these are going to be resolved by James Webb, and that's going to be important for reasons of understanding their velocity structures at the smallest scales. Like, how the hell do they stay linear and skinny for such a long time? I think that's not in the simulations, right? Am I right about the simulations there?
Raj will tell us next, I'm sure.
Okay.
Speaking of which, Raj, why don't you come set up?
Tell us how these suckers survive. So a lot of mysteries, but this is really, really cool stuff, and putting it all together for so many systems is showing us what we were seeing in the individual systems was indeed really pretty interesting. So thank you.
Okay, while Raj is setting up, I have one quick advertisement and question for you. So, advertisement is fantastic, genius graduate student. Peng's graduate student, Zurei Chen, made a really nice model which allows you to predict the emission ratios for H alpha, X-ray, everything in between. So I think it could be really fun to compare against that. And I was just wondering if there's any prospects of getting something in between H alpha and X-ray, maybe O3 or anything like that, which could also provide an interesting constraint on the role of mixing.
O3 would be kind of hard for those nearby systems. Maybe go to higher redshift, because not at least not with Muse right now. But there is going to be blue Muse, I think, right? So maybe we can see what's going on.
Okay, thank you. Let's thank her again. Thanks.
I was going to say 06 and carbon 4 would be tremendous. So a UV mission that does emission line imaging.
Yeah. Okay, great.